In this video, we're going to continue to look at the relationship between energy and work by looking at the gravitational potential energy. So let's imagine we have a basketball that is in free fall, so it is only operating under the force of gravity. And we know that force is equal to mg, and it's directed downward towards the center of the earth. Well, as the ball falls from some initial height to a final height, it moves a displacement of s. So therefore, that force of gravity is in fact doing work. And we can calculate that work like we have in the past of F times cosine of theta times the displacement s. And so since the angle between the force and the displacement in this case is 0, we know that that cosine of 0 becomes 1, and we get the force, which is just mg, because that's the force of gravity, and the displacement s is the difference in the two heights, the initial height minus the final height in this case, because of where we started to where we end. So we could find the work done by the gravitational force multiplying these quantities together. One thing to point out here, if this ball travels directly down and just falls from the initial height to the final height, that is actually no difference than if the ball travels in a different path, in that, say the ball had an initial velocity up and then traveled down in a parabolic path. We would still have the same result in finding the work done by gravity. We would have the gravitational force, which is down, and its displacement, not the distance traveled, the displacement. So keep in mind, this is completely independent of the path that the ball takes. It is purely based on the initial starting position and the final starting position, because we're concerned with the displacement, not the distance. Let's look at an example here. We have a gymnast that leaves the trampoline at an initial height of 1.2 meters, so our trampoline is 1.2 meters off of the ground, and reaches a maximum height of 4.8 meters before falling back down. And we want to know, what is the initial speed of the gymnast? Now, we could use our kinematic equations to do this like we did back in chapter 2 and 3. However, you will find sometimes it is much easier to analyze the system from an energy standpoint than using the kinematic equations. So that's what we're going to do here. We're going to look at the energy that this gymnast has at the bottom and at the top. So let's first talk about the work that's being done on the gymnast here. And we know from the work energy theorem, the work done on any object is going to equal its change in kinetic energy. And so the change in kinetic energy here is going to be equivalent to the work. Well, what forces are acting on the gymnast as it's traveling through the air? Well, this gymnast is in free fall because the only forces acting on the gymnast is gravity. And so the work done here is actually the work of gravity. And we know we can find the work of gravity by multiplying the weight by the change in the vertical position. So knowing the initial position and the final position, we can find the work done, and we can set that equal to the change in kinetic energy. Now, what simplification did we make here on the right? Well, knowing that at the top our final velocity is 0, we know that the 1/2 mvf squared goes away, so we're just left with mgh times the displacement is equal to a negative 1/2 mv naught squared. So doing a little algebra here, we can get our initial velocity is equal to the square root of negative 2g times the displacement, and we plug in our numbers, our known quantities, and we get our initial velocity to be 8.4 meters per second. Now, like I said, we could have done this without any of the energy knowledge. We could have gone back to our kinematic equations, but then that would take a few equations to get to this result, which is done much more quickly using the work energy theorem. So if the work of gravity is equal to the force times the displacement here, and notice I just distributed the mg in our equation, this brings us to the idea that when something is raised off of the ground, it has the potential to do work, so therefore we say it has potential energy. And we call this potential energy gravitational potential energy. And a way to think of this, think of holding a brick. And if you have a brick on the floor, that brick isn't going to do much work. It's just going to sit there. It's hard for that brick to exert a force on anything other than the floor that it's already sitting on. But imagine picking up the brick and lifting it 2 meters off the floor. If you were to drop that brick, it has the ability to release the energy that it had in it in smashing into your toe or hitting another brick or hitting the floor. It has the ability to do work on something else because it has height above the ground. It has potential energy due to the force of gravity because it has the ability for gravity to do work. So we call this potential energy gravitational potential energy, and that's the energy that when any object has mass and is above the Earth's surface, some relative position above the Earth's surface. And we measure that position by the height of the object, and we call h, and we typically say that the ground is our zero level. And so if we do all that, then our potential energy is defined as the mass times g times the height. So it's just mgh. Notice this is the force of gravity times the height it is above our zero level. Now, one thing to notice is we can actually make any height an arbitrary zero level. Typically, we make the surface of the Earth a zero level, or in the case of the gymnast, we can easily make the 1.2 meters above the Earth's surface as a zero level and measure all of our potential energy with respect to that level. And looking at this equation, mgh, notice that m times g, that gives us a force, which is measured in newtons. H is a height, measured in meters. That gives us a newton meter, which is equivalent to a joule. And so that, once again, draws that connection between energy and work, because both energy and work are measured in joules. So let's talk about conservative forces versus non-conservative forces and what it means to be a conservative force. So there's two different definitions that we can define what a conservative force is. First version is a conservative force is considered to be conservative when the work it does on a moving object is independent of the path between the object's initial and final positions. So this right here should throw up a red flag. That's just like what we were talking about with the basketball. We're independent of path. So it doesn't matter what path we take, it's just the initial height, final height. So gravity should start rolling around in your head as being maybe gravity is a conservative force, and we'll define those a little more clearly in a second. Version 2 of this definition, just another way to state the definition of a conservative force, is that a force is conservative when it does no work on an object moving in a closed path. And I'll give you an example of what a closed path is in a moment. So if we start and finish at the same point and no work is done, then it is a conservative force. Okay, so here's a list, and we're going to hash some of these out here in a moment. A list of conservative forces versus non-conservative forces. Your typical conservative forces are gravity, elastic potential energy, which we haven't talked about that yet. We'll get to that later. Typically from a spring or some elastic material, and then the electric force. So the electromagnetic force, gravitational force, and the elastic potential force. Those are all conservative, whereas non-conservative forces are things like static and kinetic friction, air resistance, tension, normal force, some propulsion force from a rocket. All of those are considered to be non-conservative. Let's talk about an example of version 1 of our definition, a force that is conservative because its work is independent of the path. Well, that takes us back to our basketball analogy. It doesn't matter how this basketball gets from point A to point B, it's just the important part is that there is a point A and a point B and a difference between those two. So whether it just drops in a linear path, moves in a parabolic path, whatever, it could go up, down, and then back up. However it moves, doesn't matter. The work done by gravity is still going to equal m times g times the displacement, the change in those two heights. Version 2 is talking about a closed path. So in order to understand this, think about a roller coaster and think about starting at the top of the hill. And when you start at the top of the hill, you're at a certain energy level with with respect to gravity. So you have a certain gravitational potential energy because of your height above the ground. And when you start to roll down the roller coaster, you change that potential energy into kinetic energy. And we're going to talk about that transition tomorrow in our conservation of mechanical energy. But we start to decrease our potential energy because we're getting closer to the ground, and then we go through the different paths where we increase our potential energy and decrease, and then increase, and then decrease, and then eventually get back to where we increase it up to the initial starting point, and our potential energy is still the same up there as it was when we were there the time before, because that potential energy is purely dependent upon the height. It doesn't matter how we got to that height, it just depends on the height in which we occupy. So in a closed path, if we start at this top point and finish at this top point, then our work done is zero. The work done by gravity, keep in mind here, not necessarily the network on the system, but the work done by gravity is zero because we have no change in height, because our starting point and final point are the same height. So there's no work done by gravity, so therefore gravity is a conservative force. Now you might be thinking, wait a minute, how is there no work done on the roller coaster? That's not what I'm saying. There is work done on the roller coaster, but by other forces. So just looking at the force of gravity, there's no work done by the force of gravity in this case because we end at the same height in which we started. So no work done by gravity. Gravity is a conservative force. An example of a non-conservative force would be kinetic friction. And this, once you start to think about what depends on path and what doesn't, this starts to become a little more clear. So let's think about friction. Friction is going to impede the direction of the object. So imagine sliding your hand across the table. There's friction. You have a frictional force in the opposite direction of the direction of your hand. So the frictional force is at an angle of 180 degrees, which gives us a negative F, whatever that is. You know, the frictional force, we calculate that by mu Fn, but we're not concerned with that right now. So it's just going to be a negative frictional force times the displacement. Because the work done by the kinetic frictional force is negative, and it is always negative, it's impossible to get that work back. It's impossible for the work to be positive, and there's no way for it to be zero around a closed path. And a way to see this, imagine your hand sliding across the table, and you move from one end to the other end, and you just slide down the one end, and you feel that heat heating up in your hand. And even if you slide it back to the original position, there's still that heat. It's still doing work. The direction of the force changes when you move back to the initial position because friction is always opposing the direction of the motion. So kinetic friction is a non-conservative force because that force is always going against you, whereas gravity is always pointed towards the center of the earth, and so it may be in the direction of your motion causing a positive work, or it could be in the opposite direction of your motion at times when you're moving up, causing negative work. So you can add all those up to get zero with gravitational force, but with a frictional force, you're always adding these negative quantities, so you're never getting to zero in a closed path. So the consequence of this is that the concept of potential energy is not defined for a non-conservative force. There is no potential energy from friction. And a way to realize that is think back to the brick analogy. When you hold the brick 2 meters off the ground, there's potential there. All you have to do is just let go of the brick, and it has the ability to do work on something else. It can smash your toe, or it can crush a can beneath it. So when you talk about kinetic friction, try to think of what's a way where kinetic friction has the potential to do work just by letting it act on its own. Well, kinetic friction is just something that impedes motion. It takes energy away from your motion. It doesn't have an ability to store that energy and then release it later like gravity does. In typical situations, normal everyday situations, we have both conservative and non-conservative forces acting simultaneously on an object. So the work done by the net external force can be written as the work done by conservative forces plus the work done by non-conservative forces. So think of sliding down a ramp. We have kinetic friction, which is non-conservative, and we also have a change in gravitational potential energy. So there's work done by gravity. Sliding down the ramp, we're decreasing our potential energy. The work done by gravity is positive, and the work done by friction is negative. So we can rewrite this as, using the fact that we know work is equal to the change in kinetic energy. So our total work is equal to the change in kinetic energy. And we can say our conservative work is really just the work due to gravity, because remember, we only listed 3 conservative forces: gravity, elastic potential, and our electric. And we're not going to deal with the elastic potential and electric right now. We're only going to deal with gravity. So that's our only conservative force that we could have in our system. So our work done by conservative forces is the work of gravity, and we know that that is just our change in potential energy. But keep in mind here, it's a negative change in potential energy, because if we decrease our height, that needs to correspond to a negative of the decrease, which would give us a positive work, because as we decrease our height, our force is in the direction. And so basically this negative comes out because the force of gravity is down, not up. And so using that, we can look at, well, that's our conservative work. Changing kinetic energy is our total work. So we can look at this to find non-conservative work to be the change in kinetic energy plus the change in potential energy. So this is the end result using our work energy theorem, that the work done by all of our non-conservative forces is equal to the change in kinetic energy we see and the change in potential energy that we see. So a block sliding down the ramp, we look at, well, it has a change in kinetic energy. It's increasing its energy, and it has a change in potential energy. It's decreasing its potential. So add those two together, that's going to equal the non-conservative work done on the system.